All right. What we're going to initially do is last semester we did this. Now, for those of you who are Eschenberg students, you know what that means. The people who were not in this class last semester don't. What this is the right-hand rule. I don't allow notes, but I do allow for you to have your right hand. The right-hand rule allows you to better understand vectors. It is the right way, the truly mathematical way to do it, is to take a 3x3 matrix and find the determinant of it. To which you go, what's a matrix? What's a determinant? This sounds hard. And I know it is. It is hard. What would you rather do? Something that's scary and frightening or mathy, or just simply use your right hand? Now, the way that the right-hand rule is done, for those of you who are former Eschenberg, the Eschenberg alumni from 213, you've got two vectors that need to be manipulated. The first vector, you stick your fingers, palm, and forearm in that particular direction. So if the first vector was at that wall, aiming at that wall, it would look like this. Now comes the point where the second vector, you only, let's say the second vector was towards the back of the room, the fingers only move in that particular direction. The third vector, the result of this calculation, which would have taken a 3x3 matrix and a determinant, it would naturally, the thumb naturally points in that particular direction. First vector, second vector, third. Now, one of the nice things about the right-hand rule is that only the right-hand rule, or the right hand can do this. Let's say the first vector was that way, but the second vector was at the chalkboard. I can't bend my fingers that way. It's physically impossible. I did see one student do it in the front row. She was double jointed. She just sat there and flopped her whole hand over. Those fingers touched that forearm, and I said, I think you were abused as a child. You may want to check that out. Since it's for me, for normal people, you're unable to bend it in a direction where it isn't allowed. But what you do is you can rotate your entire hand and then move the fingers in that particular direction. That's an allowed direction. So first vector, second vector, third vector. The thumb points to the third vector. On the test, a metaphysical certainty will be the right-hand rule game. For those of you who have played it before, you're like, yay, free points. It will be the appetizer problem. It looks like this. Oh, actually, that's good enough. Now, the first thing that we need to talk about are the arrows. The arrows are just pointing in general directions. Don't think of them as up, down, left, right, forward, or back. There are two other symbols. One with the circle with a dot, the other one a circle with an X. Now, some people get mixed up about this, but it's an easy way to remember. And so I know someone who has not seen this before, so I will use her in my demonstration. Now normally I would bring my magic bow and arrow. So now this is my imaginary bow and arrow. I've got the bow in this hand, I pull back the string, and I got an arrow aimed right at you. Not at you, that was last semester. But aimed right at you. What do you see? And why are you looking at the board? You should be looking at the arrow that's aimed at your head. What do you see? Only the point. light. So the one that doesn't look like the light flashing before your eyes, the one where it's the business end of the arrow is what? Is it the circle with the dot or the circle with the X? The dot. So that particular vector is coming at you. It is coming out of the page. Currently, it's aimed at that direction. Now, if she was able to steal my magic invisible bow and arrow, and you're aiming it at me, what do you see from your perspective? The little feathers, the fleshing. So the one on the right is a symbol of that fleshing. So that is a vector that's going away from you. It's going into the page. So those are two symbols. This is how we're starting to manipulate stuff in the third dimension. So up, that way, that way, that way, that way, out of the page, into the page. Now, these could be labeled all sorts of ways. The letters don't really matter. I mean, I could sit here and label all this stuff. There was one year where instead of vectors, I used city names. So it's what you call it is irrelevant. And what I'm going to do is so here are 5 problems. So typically this is just a practice session for the right-hand rule. A cross F. So what we want to do is we want to first aim our fingers in the A direction. So A, according to this, is towards that. Now F is that way. So the thumb is now naturally pointing where? C, into the page. All right. So since you're new. Yeah. You just had it in a weird way at the beginning. So A, now this is why I say this way, yeah, that way, into the page. Now, from your perspective, A, I can't bend it to F, so I got to rotate into the page. So an allowable thing to do is to rotate that wrist. Now F cross A has the same letters as the one before. It's D. So F cross A out of the board or D. Now notice one of the things that we have in vectors is that A cross F does not equal F cross A. A cross F is equal to the negative of F cross A. So if you flip the orders of the vectors, you flip the direction of the final vector. So when you flipped it, C became D. D cross B. I just did it. So F, D cross B points towards F. C cross A, did it again, F again. And then E cross A is C. So it's F, F, C. So this is the right-hand rule game. Get used to it. Probably what typically happens is it's free points on test 2. And then if enough people do well on that, then I don't include it on the final. What does happen on the final is that you have to use the right-hand rule in understanding how things work with what we're about to talk. Or we all know what I was about to say. It's too early for me to be coherent in a language. So what's all this for? I had been preparing you. The reason why I did the right-hand rule in 213 was that I needed you to start developing your sense of 3 dimensions, to start thinking in 3 dimensions. In 214, we're going to apply that 3-dimensional visualization into our studies. It all concerns about magnetism. Back in the old days, they saw how bits of metal would naturally, you'd put a little bit of this metal on like a cork, and it would naturally align itself with some mystical thing. And this ended up becoming the beginnings of compasses and understanding the magnetic field of the Earth. What's really happening on a, for normal non-magnetic materials is that you've got a bunch of atoms and the electrons around them are all orbiting in weird and random orientations. And this is, if you could go in and look at atoms on an atomic scale and see the electrons and how they're moving, all the electrons, orientation-wise, would be all different. For magnetic material, all of those magnetic fields or all those paths of the electrons are aligned, and they're going in the same clockwise or counterclockwise direction. The atoms were set in a particular way, and if they're set where they're all aligned, each atom produces its own itty-bitty magnetic field. And if you've got stuff where those magnetic fields are pointed in all different directions, the sum total is nothing. Each atom in your body has an itty-bitty magnetic field. But because all your atoms are just wandering around pointing in all these weird directions, the totality of your magnetic field is very low, if not zero. I mean, humans are just basically big bags of dirty water when you want to approximate a human body. For one of the best sources for magnetic material is like meteorites. Meteorites pass through the Earth's atmosphere. They basically become big flying molten blobs of iron, and in that moment when it's intense, they all tend to line up, and meteorites can be very magnetic. For those who are the rock hounds, the geologists in the group, go over to Lewis Hall, and there's that display case before you get to the labs of all these different asteroids. And there's one in the lower right-hand corner, and it's called the Camel's Hump. And that was a hunk of the dude who got these was kind of a meteor and asteroid Indiana Jones. He would end up in these weird countries in the 1950s and basically take stuff or pay very little money for it. And the camel's hump is this big hunk of iron, and it has these other little hunks of iron stuck to it because it has such an intense magnetic field. There was one time he had the case open and asked for me to pull off one of the magnets, and that sucker was just stuck on because that meteorite fragment was so large and it had so many aligned atoms in it that the magnetic field that it had set up just said, no, I ain't let go of anything. So for magnetism, magnetism comes from moving charge or charges. Now you could have, this is for magnetism for just materials, but if you wanted to create your own magnetic field, what's another way of doing it? Well, you create a current. A line of current has electrons going, in this particular case, from right to left. Even though the current goes from left to right, the electron flow is opposite. Yes, thank you. Even at 8:20, my brain's fudge. The way that you go, well, what's the magnetism? How does it look like in this particular way? What I have shown you with this is the right-hand rule, what I would call the primary right-hand rule. What I'm about to show you is it's kind of a weak name, second right-hand rule. And the way that I think that you guys should probably learn the right-hand rule instead of the other way. The other way is the Biot-Savart law, or Savart law. I don't know, I think it has to be French. And the Biot-Savart law uses the right-hand rule appropriately, but it's a little bit more complex. The way that I'm going to do this now is give it to you in the easier way. And you guys like the easier way. The second right-hand rule is, and sometimes I call it the wrap rule. When determining the direction of a B field next, or B field created by a current, I can't spell, I can't write, I can't think, by a current, point your thumb in the direction of the current, and the B field wraps in the same direction
And you know how I hate writing this much English. Same direction as your fingers. So now that is the great question. I need to get to that. The magnetic field if I had invented, or not invented, if I discovered the magnetic field, I would not use B, I would use M. Capital M with a little vector. Makes sense. But what happened was the dude, I believe it was Maxwell, back in the 1800s or late 1700s, who put all this stuff together. He basically saw that there were 4 major fields, and the second one was the magnetic field. And that's why he called it B, because it was the second field. And he was writing this stuff down. He created all the nomenclature and usage for this. So he called it B, and it stuck. It's not like, at first I was thinking, well, maybe B was some letter in some Latin word for magnetism or something. Sort of like why is P momentum? Well, P comes from the Latin word impetus, impulse, all that stuff. So it kind of makes sense. But for magnetism, why B? Because it was the second equation that Maxwell wrote down. Yeah, and yeah, let's just deal with it. And the unit for B is Tesla, named after the I want to say Armenian, at this Armenian Italian, I'm not sure, but early 20th century scientist who pretty much invented alternating current. So he gets his own unit. All right, so let's take a look at this line, and this is where the part comes where you're going to have to start visualizing this thing in 3 dimensions. You put your thumb in the direction of the current, so the thumb goes to the right. Now notice above the wire, my fingers are pointing out of the page. So the magnetic field on this side of the page is out. The magnetic field at that point is out, 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 out. If you curl your fingers over, on the other side of the wire, the fingers go into the page. So the B field looks like this. So as a better demonstration, if you have the wire and the current, you put your thumb in the direction of the current and see how my fingers are all coming out on the top side. So the current is out. Now if I continue wrapping, the fingers now go into the page. I would probably break my wrist if I really tried like that. So below the wire is it's going to be opposite. Now, if you took this wire and drew it like this, so that's the current of the wire. It's a lot like if we're looking at it like a barrel of a gun. If the current is like this, you put your thumb out and see how the current wraps around. So the B field is kind of like a circle. So at this particular point, the B field is like this. The B field over there is like this. The B field over there is like this. And so on. Notice how on either side of the wire, the B field is in the opposite direction, much like over here to there. So this point would be like that, and this point would be like this. So kind of like, there's the surface of the chalkboard. So it requires a certain amount of 3D visualization, which was what I was trying to do in 213. Yes?
The second right-hand rule, the rap rule, is the same thing as the Beal standard law? Is it the same thing?
The Biot-Savart law is a formal, I mean, it's a legit physics equation. And within that equation, there's a little right-hand rule thing that goes on. And what you use is, I mean, you legitimately use the right-hand rule as intended. The RAP rule, I feel, is an easier way to do things. Look it up. Type Biot-Savart law into Wikipedia and see the equation that pops up, and then you go, oh, I'm going to do the RAP rule, and heck with this. So technically, the RAP rule is not the right-hand rule, but it is a construct that helps you visualize what's going on. There is another orientation of current, and that would be the loop of current. And if you put your finger right there, align it in the direction of current, the current above the wire is out, the B field below the wire is in, and it looks like this. Or I'm sorry, like that. If you put your finger there, current left, the B field above this wire is in. If you wrap around, the fingers come out. So when you've got a counterclockwise current, the B field is coming out, inside, the B field is going in, outside. If you reverse the current, the B field flips. And you get that.
Where do you put your thumb to show for this? Like, before you thumb up?
I'll do that up on the main board. If you've got counterclockwise, clockwise, if I wanted to know what the B field was doing with this type of arrangement, I put my thumb going in the direction of the current for the lowest part of the wire. And then you see how the fingers come out in the middle, and if you wrap it around, they go in over here.
So you just always start at the lowest part?
There's no set rule to this.
Or like,
You just-
those two are not really helpful.
Yeah, for where you choose the points, it doesn't really matter. All that really matters is you put your thumb in the direction of the current at a point. You can see how it comes out and goes back in. So that has to be in. Over here, it goes in on the top, but it would wrap out on the bottom. Bottom being inside this particular point. And you can continue around the circle, and you can find out that for a circle of current running counterclockwise, the B fields go out in the middle and they go in on the outside. The reverse is true for this. Put your thumb in the direction of the current, fingers pop out above the wire here, and they go into the wire below. Over here, once again, current that way, fingers go in, and come out over there. So you could continue, I mean, you could draw multiple of these. I mean, it doesn't really matter. But it still all goes in the same direction. When you're in the problem sets, and really what I'm kind of covering is Kirchhoff's law was 1, 2, and 3. What we're kind of introducing is 5 and 8. And, oh goodness, I gotta make some corrections. All right, so this, I keep doing this every year. When you look at problem set 4, this is problem 8, the last one. And it is it's called the arrangement of currents. The one thing that I don't include are the distances 0.1 and 0.2. 0.1 is the radius of that loop. 0.2 is the distance from that edge to that line. The other thing is R1 is 0.1 meter. R1 is the inner radius. R2 is the radius of the bigger circle, and those distances are given. The numbers don't really matter in terms of understanding the material, but I do want a number, so you gotta write that stuff down. Yeah, if I hold on to that sheet, I'll post it. I'll put it up on Blackboard. Now there are, when understanding the strengths of magnetic fields, there are 2 major constructions. One is a line and an arc. If you have a point here, now all of these lines are infinite because I couldn't write this down. The B field magnitude is mu naught I over 4 pi r. I believe. I will double check that equation. I believe it's right. The r is the radius. The I is the current. The direction of the current, I'm not really big into just yet. Oh, I stand corrected. It's not mu naught I, it's mu naught I over 2 pi r. Okay. I was thinking about the arc. The arc, because I was working ahead, the arc of current, so if you have something with current I that's running in an arc theta and it has a radius of r, the arc has a B field at this center. For a line, the point could be there, anywhere along the line, the B field would still be mu naught I over 2 pi r. Where do I get mu naught I over 2 pi r? Calculus. There's a derivation. Had we if it was necessary that we use calculus, I would have formally put forth the Biot-Savart law, and then we would use it to derive this. But we're just 214 students, so just do it because I say so. That's all I can do. For the arc, it's mu naught I theta over 4 pi r. Mu naught in both of these cases is a constant, a horrible, wretched constant that I don't memorize because I have a book. And mu naught is 4 pi times 10 to the -7 Tesla meter amp. That's the constant. Will you be given this constant on the test? Yes.
It's the same constant.
For both, yeah, for both. It's actually called, if you want to look it up, the permeability of free space. But really, all that you need to know is that it's a constant. Theta is the arc angle in radians. Not degrees. So when you look at this equation, theta is in radians. So if you have this arc, or any arc, if you said you had a quarter of a circle, that arc,
We can't see Bob.
oh, side focus down. This arc would then be pi over 2. Semicircles, pi. Half a semicircle, pi over 2, and so on. Just whatever fraction of, how I tend to do it is that theta in radians is equal to 2 pi theta in degrees divided by 360 is how I do the conversion.
Do you have any reason why you don't simplify it to pi over 180?
I mean, I get pi theta degree divided by 180. Yeah, that would be fine.
No, I was just curious if you had like a specific.
It's mainly because what's a full circle? 2 pi radians. What's a full circle? 360. I mean, yeah, you could write pi over 180. It's okay. Now, circles of current are specialized arcs. A circle is an arc. What is the theta of a circle? 2 pi. That's its arc. And one of the reasons why I do this is people go, well, a line is b mu naught I over 2 pi r, and an arc is b equals mu naught I over 4 pi r. But a circle, it used to be I would write this, mu naught I theta, and then this is mu naught I over 2r. And a lot of people would get very confused and say, well, what happened to the pi? If you've got an arc and that pi is there, and you got a circle which is also an arc, but the pi goes away, where did it go? It's because theta is 2 pi. If you've got mu naught I times 2 pi over 4 pi r, the pi's cancel, and you're left with only mu naught I over 2r. The pi canceled out because the arc of a circle is 2 pi radians. That's where it went. So a simple problem would be I is 0.1 amps. It is going up. You have a circle which is, I want to get this so that it's running clockwise, an I of 0.2 amps. The distance, really what I'm doing is outlining how you solve one of the problems on the problem set. This is 0.4 meters, and the radius in the circle is 0.1 meters. The question is, what is the B field at the center of that circle? Now, if you got a circle and you got a line, you can't, you've got to find the B field at the center of the circle. If you had to find the point over here, you would have to do some weird stuff because this thing is, trust me, if you've got a circle, the easiest place to find is right in the middle. When you've got something like this, the first thing you want to do is you want to label your B fields and figure out where they're going. Yes, the radius of the little circle is 0.1. Now, I've labeled this current here in green, which doesn't really show up well. On video, it shows up great. What you need to do is you need to figure out the B field contribution by the wire. The B field, when you point your current thumb in the direction of the current, the B field on the left of this wire is up. The B field to the right of that wire is in. So everything on the left is up, everything in is negative, or is everything on the right's in. If you have a B field that is out, that B field value is, hold on, this is annoying me. There we go. If you have a B field going into the page, you put a negative sign in front of it. So the first thing that you got to do with these types of magnetic field addition problems is figure out if the magnetic field is going in or out. It's going out on the left, in on the right. The B field contribution over here is going to be positive. Yes? Okay. In fact, what I'm going to do is I'm going to draw it up on the board. This is where colored chalk would be helpful. Hopefully we wrote that in. So the B field, we've got two currents. One here going up. We've got one here going clockwise. So the first thing we want to do is figure out where the B field is for the wire. Thumb goes in the direction of the current. Fingers come out on the left. Fingers go in on the right. Use the wrap rule to figure that out. For the circle, put your thumb in the direction of the current. Fingers go in above this wire.
Wait, you drew the wrong symbol.
Oh, duh. All right. And then for this one, current goes that way. It comes out on the top and goes in there. Current goes in on the top, comes out on the bottom. So the inside of the circle has a B field that's going in. The B field out of or outside the circle is going out. So the B field contribution over here, because the wire is positive, and the B field contribution at the middle of the circle, because of the circle, is negative. So we're going to have a positive magnetic field and a negative magnetic field. Because out is positive, in is negative. Just like coordinates. Out of the page is a positive value, into the page is a negative value. Just like left, right, up, down.
Will those always match? Does that make sense?
Out is positive.
No, like the line in the circle, will those always match up? That,
Not always. Had I flipped the current,
yeah.
have it go down, left would be negative and right would be positive, and you would be adding a negative B field to another negative B field. At this point, here in the middle, you've got a negative B field contribution from the circle, because it's in the middle of the circle. It has a positive contribution from the line. Why? Because it's to the left of the line. This point is to the left of the line and in the circle. In the circle for negative. To the left of the line, in this case, is positive.
What if you flip the direction of the current?
If I flip, let's say I flip the direction of this current here. Now left is negative and right is positive.
Right.
So the B field at that point, it's a negative B field contribution from the circle, because it's clockwise. And it gets a negative contribution from the wire, because it's to the left. But that's only if this current had been flipped. So to write it down on the paper, inside the circle is in, outside the circle is positive. The total B field is B from the circle, B from the line. The B field from the circle is in or negative. The B field from the line is positive. You use the wrap rule to determine the direction of the B fields. The directions of the B fields determine the signs that you put out front. This is magnetic field of a circle. Mu naught I, I'm going to call the circle 1 and the line, well, make that 2 and line 1. Mu naught I2 over 2R. The B field at the center of the point for the circle, its distance is R. I'll call that R and this L. The magnetic field for the line is mu naught I1 over 2 pi R plus L. The current running through is I1. The distance from the line to the point being studied is R plus L. It just depends on how you label it and what values you give. Sometimes I give the total distance. Other times I give just those two parts. If I give just those two parts, you simply add them up. And then you just plug and chug. Well, I would take out a mu naught and a 2. That makes it I2 over R plus I1 over pi R plus L. So this becomes 4 pi.
Less than negative.
I lost an, oh, that's there, thank you. 4 pi times 10 to the negative 7 over 2. Negative 0.2 over 0.1 plus 0.1 over 2 pi of R plus L is 0.5.
That is 4 pi times 10.
Yes, 4 pi times 10 to the negative 7. That is the constant.
Why is it 2 pi?
Why is this 2 pi? Because it's a line. Oh, wait. Oh, no, thank you. I'd forgotten that I had already factored it out. So this becomes negative 0.2 over 0.1 is 2, negative 2. We add 0.1 divided by pi times 0.5. Divide by 2, and then divide by 4 pi 10 negative 7. All right, and I get, whoa. Oh no, I did it the wrong, hold on. And I get negative 6.1 times 10 to the negative 7 Tesla. Is that what you get? What? All right. Let me do it again. The first time? What'd you get the second time? All right. Confirm for me what the math is. If you've got a circle, I'm going to be asking about the B field in the circle. Because if you've got a circle and a line and I go, well, what's the point? And it's not in the circle, it's somewhere else. And if it's not in the middle of the circle, it's just a nightmare.
Yeah, that's what I times 10 to the negative 6.
You got 1.2 times 10 to the negative 6.
So the B field for the line, is that what's closest to the circle? Or, yeah, why don't you care about that, one that's closer to the right?
Hold on. So the first thing is that Tesla is the unit that we're going to use. Just as a frame of reference, when I first did the calculation wrong, I divided by 4 pi times 10 to the negative 7, and I ended up with something like 50,000 Tesla. All right. For perspective, the magnetic field of the freaking planet is about half a Tesla. Half. The strongest magnetic field ever made by mankind ever in its history is 7. It is not that big. If you create a 50,000 Tesla magnetic field, you are going to get a Nobel Prize. Yes, that is new physics. So when I got that answer, I was like, whoa, this is not right. What's your, the question that you had,
What's going on to the right of the line? Why don't we care about the fact that...
why do I not care about what goes to the right of the line? It feels very lonely, does it not? It's because I didn't ask. That's just it. I could have said, well, what's the magnetic field to the right of the line, 2 meters to the right? But because there's a circle on the left-hand side, none of the equations that I've given you would take that into account.
It's only feeling the stuff that's to the left.
Yeah, if you've got, now, there are problems where you've got multiple lines. And in the problem where you have multiple lines, I could ask anywhere, which in problem 8 I do. But in circumstances where there's a line and a circle, if I give a point anywhere other than the middle of that circle, say I did that on a test, line, circle, find the magnetic field over here, you know I've lost my mind. It is an inappropriate question to ask because it's just too difficult. If I had calculus at my disposal, we could kind of figure it out. You don't want to. So that's the magnetic field. Magnetic fields add together. You apply the positive and negative symbols based on your understanding of the RAP rule and how that all works. In the last things that we need to cover for this material is what we've done before is we have a magnetic field that's created by currents. In this particular setup, we're going to study the behavior of particles within a magnetic field that we create externally. How do we create it externally? Because we say so. In this particular environment, the B field is out of the page and has a magnitude of 2 times 10 to the negative 3 Tesla. The B field is out of the page within that region with a magnitude of 2 times 10 to the negative 3 Tesla.
Is this similar to your like capacitor room?
You can, I guess. It's not the same piece of equipment.
Yeah, but it's a box. With
It's a magic box, and within the magic box, I set up a rule. The B field's coming out of the page. And I fire an electron, a proton, and a neutron into this. So an electron, a proton, and a neutron walk into a bar. That bar is a magnetic field. Where do they go? What you do is these particles will feel a force, which is QVB. Q is the charge. In fact, it's the magnitude of the charge. V is the velocity or speed. And B is the magnitude of the B field. For a force on a charge that's moving at a particular velocity within a magnetic field, that would be the calculation that you do to get the force. For the direction of that force is QV cross B. Now, when you're dealing with, this is a magnitude. So really, probably the best way to write, instead of little qVB, just write big QVB and know for a fact that that Q is going to be positive. If it's an electron, make it positive. It's a proton, make it positive. It's a neutron, make it 0. But for the calculation of the force itself, the calculation of the force itself is V cross B. So a positive particle is moving up the page towards the ceiling. V is towards the ceiling. B is out of the page, so V cross B means that the force on that particle is that way. And what happens is the positive charge just kind of banks right and goes into a circular motion. Let's say we have a negative charge that is in the same magnetic field. V is still up the page. V cross B creates a thumb that goes to the right. This is V cross B. But remember, the Q here is the actual charge of the particle. Really, the important part of this is positive or negative. Here, V cross B is to the right, and it's multiplied by a positive charge.
Can't see that.
Multiplied by a positive charge, which means that V cross B is to the right, Q times V cross B is to the right, so this thing banks to the right. Again, for the negative charge, V cross B goes to the right, but the charge of an electron is negative. So it feels a force to the left. And what happens is that the negative charge banks left. So if we have these three particles, the electron banks left, the proton banks right, and the neutron is unaffected because it has no charge. So one of the things that we're building towards, we could get to this on Tuesday, is for those of you in the medicine and pharmacy pursuits, how does a mass spectrometer work? Well, the first thing you got to do is you got to separate your negative particles from your positive particles. And what's the best way to do it? You send it right through. I got 2 minutes. You send it through a magnetic field. All the negatives go one way, positives go another, neutral goes straight through. The last thing I got to introduce is if you have a wire, think of a wire of current as a string of electrons that are moving. And it's in a magnetic field external that's out. What's going to happen is there's going to be a force on this wire. And we'll talk more about this on Friday at the tutorial, so that it bows in a particular way. The electrons in this wire see that magnetic field, and there is a force that causes all those electrons to start curling in a particular direction, much like a particle in here. On the tutorial on Friday, we're going to go over problem set 4. What I've just covered is problem 4 and 6 and just 7. We'll talk all about it on Friday, 2:30.